For those who may not know of I.M. Gelfand's educational activities, can you understand me? Okay, good. It's just a quick rundown, and I'm a little embarrassed talking to this audience because some of you may have been closer to the events I describe than I have been. So if you have a correction or an addition, please feel free to interrupt. And as some of you may know more about this topic, my talk will emphasize my work with him here in the U.S. rather than his work more generally. Gelfand's most abiding educational activity was his school by correspondence, which he started in the 1960s in Moscow. I think it likely that he did it because of his own background, which, as you saw, he grew up in a shtetl in Ukraine with few intellectual resources. By all accounts, he was a prodigy who had to invent his own supports and wanted to reach out to children across the Soviet Union who may want for mathematical stimulation. So let me stop here first and ask, have any of you participated in Gelfand's school by correspondence? Okay, good, then I can feel like the expert. Okay. The school was a great success. Lots of students around the country participated, and it meant a lot to him that he could provide such students with a good mathematical support. So when he emigrated to America, it was on his agenda to continue the work, adapting it to the American experience and also to the correspondence format to electronic communication. The most important fruits of his work was of our work together with this book on trigonometry, the fourth in a series written for the school by correspondence and translated into English. I would come to Rutgers every Tuesday and work with Gelfand on the trigonometry book. He took great pride in the fact that, unlike many mathematicians, he talked about pre-college teaching through his own experience. And he often expressed his gratitude that I lent him my own experience with American high school students, which in his own words he said he badly needed. It's also remarkable that he took extreme care and spent much effort on the tiniest detail of exposition for high school students, as much care and effort as he spent on his books for undergraduate, graduate students, or for a journal article. Have any of you worked with him? Oh, good, I can continue to talk as an expert. He was as demanding of himself as his colleagues. That's the main thing. Once, on reviewing some chapters, he commented, "What a long, boring book," after we had spent months refining the work together. As critical as he was of others, he was more critical of himself, a criticism born of humility and a remarkable sense that whatever he did, the edifice of mathematics loomed higher than any of our own experiences. Another time we were talking about mathematicians who might be interested in one work, he mentioned some names. This one is an algebra, that one is a number theorist, and he continued, "I am an analyst," and then he said, "a good one." And if you look at the list of his prizes, you can see the kinds of things that he didn't need to talk about that. Most of our work consisted of my writing and him criticizing. Luckily, I have a pretty strong ego and always took his criticisms as positive. Later, I would find out that as much as he complained about my work, he would praise me to the skies to other people. And that is, you heard the worst from him directly, and others heard the best about you from him. For many people, it's the other way around. Our work also followed a pattern of interaction that I found common in my work as a teacher of mathematics with mathematicians. Typically, I asked a question, sometimes that students commonly asked, and Gelfand knew the answer right away. It wasn't always an easy question, but because of his deep understanding and experience, it was easy for him. But he had not thought of the question. That was my job. He would often say, "It is a correct question." Those were his exact words. So a typical pattern, I'll just show you one. It's just a little problem. If sine A equals 3/5, find sine 2A. Well, it's not so difficult. Sine 2A, there's a formula. And it involves the sine and the cosine, and you can get the cosine from the sine. And so sine 2A is 24/25. In other words, and this is not well known, one acute angle of a 724 right triangle is double an acute angle of a 345 right triangle. Which is very interesting. Well, he enjoyed this problem. Then he commented, this shows an interesting phenomenon. There are certain angles whose sines and cosines are both rational, the ones in the Pythagorean triples. If this is the case, any integer multiple of such an angle shares this property, and even the sum of two angles shares this property. He said that right away. Later, another mathematician commented that this shows the set of rational rotations forms a group, and so on, from this very simple problem. That was the kind of way his mind worked. Another time we were working on a chapter in graphs of trigonometric functions. In his typical style, he used this topic to introduce Fourier series. I had shown him a math contest problem about getting, where is it? There it is. Getting the maximum value of that function. Well, the 3 and the 4 invites you to introduce a 5, and you see that f of x over 5 is 3/5 sine x plus 4/5 cosine x, and 3/5 and 4/5 can be the sine and cosine of a certain angle. And so you can write f of x over 5 is cosine theta sine x for a certain theta, plus sine theta cosine x, which is sine x plus theta. So the sine function is never greater than 1, so f of x can't be greater than 5. All right, so much for that. But what he said a little bit more. He said immediately, the main idea is that for any angle alpha, the function sine x plus alpha is a linear combination of sines and cosines, or a linear combination. This means that the basis sine x and cosine x for Fourier series need not be changed if the function being represented is translated, since the addition formulas almost define the sine and cosine function. This means that they are the best functions to represent all periodic functions, all from this little problem. There's more than this to this story, and this is typical of our interactions. I would feed Gelfand a simple problem or a simple question, and he would discern within the question a profound or advanced mathematical topic. Well, I hope this gives you the idea of what work with him was like, but there's a bit more. I haven't talked about the joy he would take in the simplest mathematical connection. Once we came across a list of formulas, sine 2x, sine 3x, sine 4x, and so on, and they're not so difficult to derive, and even a general formula is not so hard to get, for example, from de Moivre's theorem. But Gelfand was more interested in how the formulas betrayed their origins, which ones had even or odd powers of sine x, patterns in the coefficients, and so on. That is, he was taking a student's eye view of the situation. What would a naive student see in this list of formulas? The results were fascinating to listen to, but more fascinating was the delight which he took in the exercise. He used to take his hands and put them between his knees and clap his hands and knees together at the same time in the same way that a young child would given a toy or something like that. This was, and as you can imagine, this was a little bit contagious. Another important point about his work in education is how much pride he took in the accomplishments of his students. One of the last times I visited him, he had a pile of books and reprints and delighted in showing how his students have contributed to the field. But the relationship was a little deeper. It was a joy in the knowledge of itself, as the pride of a parent can be for the child itself and not just for the parent's role. He had taught them how to think and how to investigate things mathematically. But he remained with them, it seems, even on the next lowest level, the level not just of processing ideas, but of the particular ideas themselves. His mind overflowed with them, and he seemed to have had the ability to surround himself with people who were also worthy receptacles, who ensured that the abundance of ideas does not fall on parched earth. It was on this last occasion also that he gave me perhaps his last lesson, both in mathematics and pedagogy. We were talking about a proof of the Pythagorean theorem that appeared in our trigonometry book. Gelfand said, "We must rewrite it. It is wrong." I asked for details. His hands fluttered over to a pencil. He was in bad shape medically at that point, and began drawing. His lines were wiggles like the outlines of the aged elephants, if you've ever seen the Barbar books. But I knew what he was drawing. He was drawing this, a large square, and then 4 triangles and another square inscribed in it. You connect the points, and you can derive from this that a squared plus b squared equals c squared. You see, the big square is a plus b quantity squared, and that's 4 times half ab, which is the 4 triangles, plus c squared. And if you write it out, you get the Pythagorean relationship. So I knew the proof, but somehow he was talking about something I didn't see. He was silent for a minute. He used to fall silent a lot, sometimes for many minutes, to think about something. One learns patience with this seeming antisocial behavior. Sometimes, after the silence, he would walk over to the phone and make a call, or read some email, or take a book from the shelf and show me a poem of Pasternak. His mind often behaved like a magnificent wild animal, which he was trying to use as a beast of burden. Eventually, the flow of conversation would return, but one never knew how or when. My patience eventually paid off. He broke the silence. He said, "It is wrong." I didn't see the error. He smiled a bit, and his eyes lit up. He loved the intellectual cat and mouse game, a game which portrays the art of a master teacher. I knew what's coming. He would tell me as little as possible until I got the idea myself. How could this be classic? This is a classic proof. How could it be wrong? Is he getting a little too old for mathematics? Of course not. I was wrong. His hand took up the pencil and drew a diagram which eventually resolved itself into 2 right triangles symmetric about a line with the same hypotenuse. He said, "When are 2 triangles congruent?" Uncharacteristically, he answered himself, "When they can be made to coincide." He used the word sovpadati. He didn't know the English word. With a gesture whose irony will unfold with the dialogue, I agreed, placing my right hand exactly over my left. He said, "These 2 triangles cannot be made to coincide. You must reflect one to get the other. There are 2 definitions." I know what he's saying, but not why he's saying it. We had talked years ago about orientation in the plane and how areas of polygons can be given a sign according to the orientation of their perimeters. The subject had arisen with the discussion of Hero's formula. But what does that have to do with the proof at hand? I didn't understand, and I told him so. The 4 triangles in the diagram all have the same orientation. Even if you don't allow for reflections, they can be made to coincide. You don't need to flip. Doesn't he see this? I knew better than to ask him that question, but I had a mental reservation. Happily, I also had some patience. Gelfand had more patience. He looked at me. The teacher in him knew that I would eventually figure it out, and that the process would do me more good than if he told me what he was thinking. This was his gift to me, a gift of knowledge and of patience and of trust. He could have shown me his idea directly. Instead, he let me discover the insight and demonstrate his gift both as a mathematician and a teacher. Look, I said, you trace this triangle clockwise, then you trace the next one clockwise. A rotation brings one onto the other. There's no need to flip. I said that. He was not impressed. He merely asked, rotation about what point? There was some ulterior, that was too easy a question. There's some other reason why he said that. Around this one, and I indicated the center of the square. Easy. Then suddenly I saw what he was seeing, and I mentally gasped. The triangles indeed have the same orientation. But if you trace the triangles in a counterclockwise orientation, as they are there, the four hypotenuses form a square with a clockwise orientation. So the areas are equal only in modulus, he said. We have to count for this in our book. He said a few more things, but the words are inconsequential in comparison with the lessons, both mathematical and pedagogical, that I had learned. I thought of other dissection proofs. There are other dissection proofs which don't involve this problem, and we adjourned and so on. The point is that he was a master of the art of teaching, not just the science of mathematics. Thank you very much.